So, having discussed about the macro states, micro states, and then solving one or two problems regarding how to calculate the number of micro states and for a given macro states, as we will see that we have seen that if you have very large number of particles and this number of micro state is going to shoot up like anything. So statistical mechanics, to deal the problem from the point of view of statistical mechanics, we need to have certain rules to deal such a large number of microstates. So basically now in this video and few videos following this, we will learn about some of the laws that being followed for the statistical system, right? So before we go into the details about these laws, which we can call universal laws of statistical system, so let us get familiar with this, some of the basic concepts, and most of you all probably know about these things in earlier classes as well. So first is degrees of freedom. Okay, so now let's consider one of the simplest system, which is, let's say, monatomic gas, and it consists of, let's say, n particles. Okay, so the system, we know the energy expression for the system typically consists of let's say f coordinates of position and then f coordinates of momentum. Okay, so for each molecule, so I say that there is f degrees of freedom. Okay, for per molecule you can think about the degrees of freedom of the system per molecule is f, since it consists of n number of particles. So I will say that the system has got nf degrees of freedom. Okay, so the system has got nf degrees of freedom. Okay, so assume these particles to be meaning non-interacting, or these are independent particles. Okay, and these are classical particles. All right, so basically what you need to think about here is that if the system has got nf degrees of freedom, means that so there are n particles and the energy expression has got f number of coordinates of for the position, and then similarly f for the momentum. Okay, so next concept that you need to familiar with, there is a position space. Okay, so again you consider the simplest system. Okay, so you have got n particles distributed in, let's say, volume V. So, and let's say consider this static system. Okay, so let's simplify our system. Let's say it's a static system, means what? All the particles in the system are static, all are at rest. So I can represent the system, okay, using, let's say, I want to know about the system, so all are static, so I can have a Cartesian coordinate system. Okay, so which I can sort of x, y, z axis, which are independent and mutually perpendicular. So if there are n particles, so then I can represent like each of them like wherever they are thinking about. Okay, so it could be anywhere in any of this quadrant. Okay, so and which are distributed in a volume. You can think about, let's say this is my volume V. Okay, so this space, which is governed by these three mutually perpendicular axes x, y, z, okay, it gives you complete information about the system. So where each of them, these particles are located. Okay, so that's why this space is known as position space. Okay, so this is for a static system. So now consider okay, and let's say the smallest volume element you can think about in this position space, which I can write as, let's say, dv will be equal to dx. So dx is let's say smallest element along dx. I can think of similar dy dz. So the smallest volume element in the position space, I can write dv equal to dx into dy into dz. Okay, So basically here each of the particles are represented as they are using their position coordinates. Okay, so and this is three-dimensional, as you can see here. Okay, so yes, so the same thing is being written here. The three-dimensional space in which location of a particle is completely given by the three position coordinates and which are mutually perpendicular axis, okay, and independent in fact. So and a volume element is given by this particular which we have a particular expression which we have already talked about in the previous slide. Okay, so if we have, let's say, dynamic system, okay, so let me just copy this particular expression. Okay, so if I hope I can copy, so copy, okay, paste it here. Okay, so again I have this system. Okay, so now let's say instead of static system, the same system that we have considered, now this system is a dynamic system. So the particles are moving. Okay, to describe the system completely, okay, the position coordinates are not enough because each of these particles are associated with some kind of velocity. So each of them, they may be moving randomly, okay, so but each of them associated with certain velocity. So I need velocity axis as well. Okay, so Vx, Vy, Vz, then only I can describe this system. So for simplicity, let's consider the mass of each of these particles, let's say m. So mass of this particle, let's say m. So I can have momentum px. Okay, I'm talking about the simple one particle system which will be easier to understand, which can be replicated for other particles as well. Okay, so this is mvx. Similarly, you can have py, mvy, then it is pz. Okay, so to know the momentum of the particles, so I can represent the momentum of each of these particles, okay, in a in another space, okay, which I can draw. Now again, let me draw. Okay, okay, so let me just complete this. Okay, so I can have similar earlier similar to the position space, I can have, let's say, this is py axis, px axis, pz axis. So I can represent the momentum of these particles in this space. So this space is known as momentum space. The space spanned by this momentum axis, which are again independent and mutually perpendicular axis. And if I have n particles, then I will have n representative point for each of them, and which each point is representing the momentum of the particle. All right, so this dynamic is about the velocities or the momentum of the particles will be given by this momentum space, whereas the position space will give you the location of each of this point. But now to describe the entire information about this, or the complete information about the dynamic system, so I have to combine both this space, position space as well as momentum space, then only I will get the phase space. Okay, so to know the entire information about the dynamic system, I need what is called as phase space. So this is a combination of position space and momentum space. Okay, in momentum space, as you can see here, similar to the position space, this is also three-dimensional. Okay, this is also three-dimensional. So then naturally your phase space will become six-dimensional for the Cartesian coordinate system that we have considered here. Okay, so it has become six-dimensional. Okay, and volume element in position space, we have seen that dv equal to dx. So the smallest element we can consider in position space, dx, dy, dz. Okay, similarly in momentum space, I can consider dpx, dpy, dpz. Okay, so for the phase space, the momentum element is typically represented by d tau, is a product of all these quantities, dx, dy, dz, dpx, dpy, and dpz. So this will give you the volumetric element. So the point on a phase space, say this is a 6-dimensional space. Okay, so it's not possible, it's very hard to represent on it's hard to even imagine, think of a 6-dimensional space where each of the axes is mutually perpendicular. Okay, 3 of them are position axis, this is the coordinate axis, and 3 of them are momentum axis, and all of them are mutually perpendicular. Okay, so what I can do, I can have a representative coordinate axis to represent momentum and the coordinates, which I will talk about in minutes time. Whereas let me continue, what is this phase space? So phase space, the point in the phase space gives you the complete information about the particle. Okay, so its position as well as the velocity. Okay, so basically when a particle moves, so its momentum will change, maybe its location will change. Okay, and then that point will move in phase space. Okay, so let's see what is written here. Yes, so the complete information about the dynamic system can be known from the phase space. Okay, and then the smallest or the small element in the phase space, as I talked in the previous slide as well, is given by this particular expression. Okay, so before we go to mu space and gamma space, I have to talk about the phase cell. Okay, so again let me draw this representative. So see, the phase space is 6-dimensional. So then I have, let me just draw one. So on this on this screen or on paper you cannot really draw all this 6-dimensional space. So I have a, let's say I take this 6-dimensional space, okay, a sheet of that space, meaning you will see what I am trying to do. Okay, so here I am trying to draw, let's say it's a x-axis, and let's say the momentum along the x-axis. So px is a representative of the momentum axis along the x direction, and other in the coordinate axis x direction. So basically this x and px is representing a energy sheet, because the energy of the particle or the system is typically represented by, you can think about like px square py pz by 2m, which is equal to p square by 2m. Okay, so from this expression you can think about the momentum representation is also gives you the energy of the system, or energy of the states of the system. Okay, so okay, so here is a energy sheet in the phase space given by this x and px axis. So what I can do, I can divide this phase space, okay, energy sheet into further small okay, elemental area, let you can think about, okay, along the px and along the, let's say, x direction. Okay, and let's say, just I am exaggerating here, let's say from here, sorry, so let's say from here to here, this is dx. Okay, the infinitesimal the distance along x-axis. Similarly I can have, so let me consider this box, okay, this, okay, so similarly along the momentum I can have dpx. Okay, so this is this this representation, so this you can think about energy sheet. Okay, this is like your energy sheet. Why I'm calling it? Because this gives you the energy of the system, let's say along x, so to say x momentum, right, momentum along x axis, so the energy associated with the x direction. Okay, similarly on other side here we can get the location or the coordinates of the system or the particles along x axis. So the point on, so this smallest volume that you can see, the box that you have see, this is called as phase cell. Okay, so now the point within this phase cell represents state of a system. So this system, if a system moves, this phase point will move in this energy sheet. Okay, if at all, if it moves, if there is a change in the x and the px values of the system. Now from the classical point of view, this area of this smallest the element or the phase cell can be arbitrarily, it can be reduced to 0. Okay, so let me just write it, dx, so the area of this phase cell will be given by dpx. Okay, let's say it's equal to h naught. Okay, so from the classical point of view, this h naught can be anything. It can be arbitrarily make it so small that, you know, if at all, if the phase point moves within this cell such that there is no instrument to measure any changes in the system accurately. Okay, if there is a slight change in this phase point. However, so in principle I am saying that this product of, or the area of this phase cell could be made it to 0. Okay, I mean arbitrarily it will be as small as possible. Whereas in quantum mechanics doesn't allow you to do that because of the principle of because of this uncertainty principle. Because from the quantum mechanics, what happened, the minimum product of this dx, so in quantum mechanics, what will happen, this dx dpx minimum is actually h, which is Planck constant. Okay, so this, so you cannot choose arbitrarily as small as you want. This is the area of the phase cell. Okay, so there's a limit to it. Okay, so now, so by gathering all this information that we have learned here, so the volume element or the minimum size of the phase cell we can have, so that this d tau that we have talked about here, see this dx into dpx will give you 1h. Okay, dy, so similar to dx dpx, the dy and dp will give you one more h, the minimum volume that you can think about, or the minimum area for the in that energy y energy sheet. Similarly, sorry, here dx is written, so this has to be dz. Okay, so this dz and dpz will give you another h. So the smallest element in the phase space which you can consider is actually hq. Okay, so it is this I have talked about the minimum size of the phase cell. So phase cells are the smallest compartments or the partitions that I have made into this phase space. Okay, and here I have drawn only one energy sheet and just a representation of the entire phase space. Okay, then let's come to mu space and the gamma space. Now again, let me see if I have the based on, yes. So I have this position space which I have already talked about. Okay, so so probably this will not do the job for me. Let me just to represent the phase space, what I have done. So let's say this is a representation, this is x. Okay, so this x, think about this is a representation for all the coordinate axes. Okay, because phase space is 6-dimensional, hard to represent. So and this is px, which think about this is like a representation for the momentum axis. Okay, all three of them somehow. Okay, think about it. So when I have, let's say, one particle in phase space, what I do, let's say sorry, so this is like, let's say, one particle I have. Okay, I have only one particle system, so I can represent it in, if particle is moving, it's a dynamic system, so I can represent by with one point in the phase space. and as a air is moving, this point will move in the phase space. Okay, now if I have n particle, okay, so then I will need n such point to represent the entire system. Think about this. Okay, so now this representation is known as mu space or the molecular space. Okay, this is mu space. This is mu space or molecular space. Okay, where each the location and the momentum of each of them are represented. Okay, meaning shown in this. So each point, so there are n particles, means there are n points in the space, in the mu space. Okay, and it is 6-dimensional. It has position space plus momentum space. So that's why 3 from the 3 dimension coming from the position space and 3 from the momentum space. Now the same n particle system can be represented in another way. Now think about shifting all the information about these n particles to some axis. So imagine now representing the same system into axis. There are 6 n dimensional space. Okay, so what I have done here, so this mu space was 6-dimensional. Okay, 6D, let me write it, and it had got n points, and because I have considered n particles, so that's a n points in the phase space. So this entire n points system, I'll represent this by single point, whereas my axis now became how many? 6 of them. So again, let's say this px I am representing here, but this, as I told you earlier, this is px is a representative for, is a representation from the all the momentum axis. Similarly, this x is a representation for the entire coordinate axis. So like I have 6 n dimensional space. Okay, so this is, you know, the entire n system consisting of n particles, all the n, meaning is within one point. Okay, so now this, so there is slight difference. So in the position space, in the mu space, I had, if it is a, so first let's fix the system, let's say n particle system. So in position space, it will have 6-dimensional, so there are n points representing the system, whereas in the gamma space I have now 6 n dimensional space and entire system is represented by just single point. Okay, so this will be helpful when I talk about meaning the macro state, which represents so many micro states of the system. So now let's try to summarize this whatever we have learned. So for, let's say, for a system f degrees of freedom per particle, so then system will have, you know, if there is n particle, nf degrees of freedom. Okay, so if we have, let's say, single particle, then we have position space of f dimensional, meaning if there is a f degrees of freedom. So if I have, if f is 3 in that case, so it will be 3-dimensional space, and the momentum, similarly we have f dimensional if there is f degrees of freedom per molecule. So you can consider this f to be 3, and then things will be, I think, much more easier to understand. The mu space, it's a combination of position space and momentum space, so that's why it became twice f dimension. Now in gamma space, what we do, we entire system we represent by one point, and everything is we shift it to the axis. So that's why we have, it will be decided so this dimensionality of the gamma space depends on the number of particles as well, as you can see here. So that's why it will have twice f dimensional space.